All right, so today we're going to start the acid-base part of equilibrium. Today we're just going to kind of review some of the acid-base stuff that we talked about last year, and maybe a couple of new things here or there, but yeah, for the most part, just really reviewing kind of pH, pOH, what's an acid, and what's a base. So, properties you should know, because there's almost always one really simple, straightforward question on the diploma that covers this. So, acids taste sour. They react with most metals to produce hydrogen gas, right? They're going to bubble. They are going to turn blue litmus red. The red will stay red. They conduct electricity, and they're able to neutralize a base. So last year in Chem 20, we talked about two different definitions of an acid. We talked about an Arrhenius acid. That was kind of our original definition. We said that those contain hydrogen, and then they are going to give off that hydrogen ion, also known as a proton, when they are placed into water. Then we talked about the modified Arrhenius acid. We said, you know what, hydrogen ions don't actually exist. We actually find that the hydrogen ions are going to attach themselves to water and they're going to make hydronia. So we changed or modified the Arrhenius to say that we're going to react with water and produce hydronia. You're going to find in Chem 30, I don't want to say we use a bit of both, but we kind of use a bit of both. Sometimes if we're reacting with just water, we're going to use the modified Arrhenius. But sometimes we're also just going to say that the proton concentration or the hydrogen ion concentration is some number. And you need to make sure that you can recognize that H plus and H3O plus are the same. So if I'm given one, I can safely assume that I'm given the other one as well, okay? All right, bases. So properties of bases. Bases taste bitter, they feel slippery, they turn litmus blue. They also conduct electricity because they also have ions in solution, and they are going to neutralize acids. So red litmus turns blue, blue litmus stays blue, right? So make sure that you recognize the distinction there. Make sure that you're also capable of recognizing that if I dip litmus paper and I see no change, I shouldn't automatically assume that it's an acid or a base. I do want to do the second test because it could also potentially be a neutral substance, because neutral substances don't change either color of litmus paper, okay? Our definitions. So we talked about an Arrhenius base, and this was something that contained hydroxide. So sodium hydroxide, magnesium hydroxide, those are kind of what we call classic bases because they all have hydroxide and are super easy to recognize. Then we talked about the modified Arrhenius base. We talked about this when we got into some compounds that didn't really do what we expected them to do, right? And ammonia is kind of the classic example that we talk about in Chem 20. Same with sodium hydrogen carbonate or baking soda. And so what we find with those is they don't contain hydroxide, but we can clearly see when we test their pH that they are basic. So we modified our theory to say that it's a substance that dissociates or reacts with water to produce hydroxide ions, right? So the common point is we are producing hydroxide ions. The question just comes from how are we doing that? Are we doing it because they already contain it? Or are we doing it because they're actually reacting with water and producing hydroxide in that manner? So this year we're going to look at a whole new definition. We are going to look at the Bronsted-Lowry definition. This is going to be the definition that we predominantly use in pretty much all of our K calculations, right? We saw K calculations in the last unit. Now we're going to be doing more K calculations, but specifically for acids and bases. So Bronsted-Lowry theory is what we use when we are dealing with equilibrium system. So when we are looking at this particular definition, a Bronsted-Lowry acid is a substance that can donate a proton. So your acid doesn't really change. You're still looking for what has the H's. That's still going to be your acid. It's your base that really changes, right? Because we're used to bases either having hydroxide or making hydroxide. In the Bronsted-Lowry definition, it really has nothing to do with hydroxide. Okay, so in the Bronsted-Lowry definition, what we are looking at is a substance that can accept a proton. So we're going to be able to put a proton onto that particular substance. Again, remembering that a proton is a hydrogen ion. So we're basically looking at that hydrogen ion moving from the acid over to the base. So acids are known as proton donors. because they're going to give off the proton. And bases are known as proton acceptors because they are going to take that proton, okay? So what that means is when we write our equations, you're going to find it's going to look a little different, right? Because normally we do like an acid plus water or a base and water. We might still have that, but the difference is now going to be that every equation that we write, let me just put this in at the bottom, maybe a different color so it stands out. We're always going to have our Bronsted-Lowry acid combining with our Bronsted-Lowry base, right? So this looks a little different because we're used to having an acid with water or a base with water. We're not used to putting the two together. But in this case, we're going to put the two together. So we're going to have the Bronsted-Lowry acid plus the Bronsted-Lowry base. And what you're going to find happening is the acid is going to start with an extra hydrogen, but then when we get over to the product side, it is going to lose that hydrogen. Okay, so I guess showing you a real example instead of just writing some stuff out. Let me just make the font a little smaller so it's not so massive. So let's say we have hydrofluoric acid, right? It's HFAQ. And we react it with, I don't know, let's go with a nitrate ion. So NO3 minus. Okay, arrowhead. These are going to get double-headed arrows because we're in the equilibrium unit. So what's going to happen? Well, first I need to look at this and I need to decide what's what. So I know because I'm in the acid-base unit, one of these has to be the acid, one of them has to be the base. Generally, you guys don't really struggle with this. It's usually pretty easy for you to recognize, right? You look at it, you're like, hey, this has a hydrogen, therefore this guy has to be my acid, right? So that's going to be my, sorry, fonts are being all wonky. This is going to be my Bronsted-Lowry acid. And it's going to be the Bronsted-Lowry acid because it has the extra H. Okay, that means the other one, the nitrate over here, it has no H. So this is going to be my Bronsted-Lowry base. So what's going to happen as this reaction occurs is we are going to take the hydrogen from here and we're going to move it to here, right? Because we said, according to the definition, a Bronsted-Lowry acid is going to donate a proton. So it's going to lose the proton. And the Bronsted-Lowry base is going to accept that proton. So product-wise, we are going to create an F minus, because it lost the hydrogen, along with HNO3, because it gained that hydrogen. So product-wise, we do also have names for these products, okay? When we are naming them, we tend to call them conjugates, okay? So Bronsted-Lowrys are usually the reactants, and conjugates are usually what we are talking about over here on the product side. So this is a conjugate, and this is also a conjugate. Okay, and when we talk about conjugates, we're going to revisit this again later. We talk about our species as existing in conjugate pairs. So when we are talking about a conjugate pair, it's always going to consist of something from this side of the equation paired up with something from this side of the equation. So when we talk about a pair, I'm going to pick two things from opposite sides. How I'm going to decide what to pair it up with, right? So either I'm going to pair the HF with the F, or I'm going to pair the HF with the HNO3. So how I make the decision of what to pair with what, according to our definition of what a conjugate species is, it should relate to the original one, and the only difference should be that it's missing or has an extra hydrogen. Right? So we're dealing with conjugate pairs. We're looking for something that either has an extra hydrogen or is short a hydrogen. So based off of that, if I have HF over here, its pair would either be like an H2F, although that would never exist, but let's just say it would be an H2F because that would have an extra H, or it would be just an F because that's the difference of either having an additional proton or short a proton. So what that means is over here, our HF is going to be paired, sorry, that's a horrible line, with F minus. So this F minus is going to be a conjugate species. Because it is related to the acid on this side, it is going to be a conjugate base. So the acid gets paired to the conjugate base. The difference between the two is that this has a hydrogen, this does not have a hydrogen. Now we also need to pair the other one up. So the nitrate is going to pair with the HNO3. Because again, this doesn't have a hydrogen, this does. They both have that nitrate component that is the same between the two of them. So out of the pair, this one has the H and this one doesn't. So we said on this side, this was the Bronsted-Lowry base. That means over here, the HNO3 is going to be my conjugate acid. Okay, so you're always going to find that you're going to have an acid plus a base. And you're also always going to find that on your product side, you're always going to have an acid and a base. That's always going to happen when we're writing Bronsted-Lowry equations. Okay, we're going to be transferring the proton over, which is similar to what we did before with all of our acid equations that we wrote. But now we're transferring it in a slightly different way. Sorry, I'm getting all these text messages from people and it's disturbing my video skills. Okay, so hydrogen's going to move over. We're not going to have it over here. So these are pairs because they both have the F. These are pairs because they both have the NO3. Out of my pairs, I can decide which one's the acid because out of HF and F minus, the HF has the extra H, the F doesn't. Same deal with the HNO3 and the NO3. The HNO3 has the extra H, the NO3 does not. Okay, so that's the acid, that's the base. It's always an acid and a base on one side, and an acid and a base on the other side. Okay, we are going to come back and revisit all of this conjugate acid-base stuff as we go through the unit, okay? I think the next slide might actually give you a little bit more of a breakdown of a diagram, right? So here's kind of a classic acid. You're going to find that most of the time in Chem 30, we are never going to talk about hydrochloric acid. Or if we do, we're not talking about it in the context of equilibrium. And the reason for that is hydrochloric acid is a strong acid. This reaction goes to completion. We use a single-headed arrow. When we use a single-headed arrow, that means this isn't equilibrium. The purpose of this unit is acid-base equilibrium. So what that means is when we are talking about acid-base equilibrium, for the most part, we're not going to be talking about strong acids because strong acids and strong bases go to completion. They don't reach equilibrium. Okay, you're going to find as you work through your booklet, today's stuff is all going to be on strong acids and bases, and that's just because we want to make sure we review them. We want to make sure that we remember how to do all our pH and pOH calculations, and we also want to make sure that we're able to recognize the difference between what we do for a strong acid versus what we do for a weak acid, right? So if you think back to last year in Chem 20, everything we did was for a strong acid, right? Everything we did had a single-headed arrow. We were able to do stoichiometry, which makes sense because that's what we do in Chem 20. We do stoichiometry. Now, Chem 30, today we're going to look at those systems, but starting tomorrow, which again is going to be by video because I'm going to be home for the next 2 weeks, you're going to see that when you are watching it, we're going to be making ice tables because our reactions don't go to completion, okay? So this talks a little bit more in these notes about conjugates, so we kind of already talked about that in the last slide. Again, we are going to revisit that in some later lessons. So reviewing your calculations from last year, right? You had to memorize them last year. You still want to make sure you know them for this year because they're not going to be provided to you. So, oh, I'm missing a negative here. Hold on. Should say pH equals negative log of hydronium. pOH is negative log of hydroxide. Then we have our equations to go the other way. So we have that the concentration of hydronium is equal to 10 to the negative pH, and our concentration of hydroxide is equal to 10 to the negative pOH. We then had our equation to allow us to switch between the two, right? So pH plus POH equals 14, and that's going to let me alternate between the two depending on what I need. How you decide what you need: if you have an acid, you need pH. If you have a base, you need POH, right? And that's because when I have bases, my dissociation equation is going to involve hydroxide. So I need to make sure that I'm dealing with POH, right? But if you remember back to last year, when we're in the lab and we're measuring things, we only have pH meters or pH paper. We don't have POH meters or POH papers. So you're almost always going to be given a pH and then asked to convert it. So looking at some examples from last year, or maybe not quite yet, apparently I'm going to talk about polyprotic acids. We're not going to look at calculations really too much for polyprotics. If we do, we're only going to look at one step, right? So remember when we talked about polyprotic acids last year, we said these were acids that had more than one hydrogen, that they were going to ionize in a stepwise fashion. So if I had two H's, I would have to write two ionization equations, one to remove the first hydrogen, and then another one to remove the second hydrogen, and then kind of go from there, okay? So for today's stuff, we're only going to be dealing really with the strong ones that are monoprotic. Okay, we're also going to talk throughout this unit about species that are amphiprotic. So this is something kind of completely different than what we talked about last year. Last year we said either something was an acid, something was a base, or it was neutral. When we deal with the Bronsted-Lowry theory, we start to realize that this isn't quite true. And some of you will pick up on this. Some of you will see as we write equations, something like water does some wonky things, right? So if you think about water, sometimes we react it with something and we turn it into hydronium. But other times we take water and we react it and we turn it into hydroxide. So if you think about the two definitions that we just talked about, the Bronsted-Lowry acid and the Bronsted-Lowry base, we said that the Bronsted-Lowry acid was something that was going to donate a proton, right? So in some situations, we see that our water is going to wind up turning into hydronium. And then in other situations, we see that our water is going to turn into hydroxide. So these are both water equations, but in these equations, it's doing something different. So in this one here, if we look at this, this had two H's and this had three. So we just gained a proton. So if you think about the definition, it's a Bronsted-Lowry base that is going to gain a proton. But here, when we look at the second one, water turned into hydroxide. So it now has one less hydrogen. So it is a Bronsted-Lowry acid. Sorry, I'm making weird faces because I can hear my husband coughing in the background. And now I'm getting more paranoid as I sit at home. It's fun times. All right, so here we have an acid and a base, and it was both water. So what that means is water can do both. Water can be an acid and it can be a base. So this is what we call an amphiprotic species. So an amphiprotic species is a substance that has the ability to be both an acid and a base. Doesn't mean it's going to do both at the same time. Water will, because water is special. But most of the time we're going to find that whether it's going to behave as an acid or as a base is going to depend on what we combine it with. If I combine the amphiprotic substance with something that's an acid, it's going to have to behave as a base. If I combine it with something that's a base, it's going to have to behave as an acid, okay? So things that tend to be amphiprotic. Well, you should be able to recognize one already. It's water. The other ones that are amphiprotic are species that have a hydrogen and then some form here, and then they have a negative charge, right? So like HCO3 minus or HPO42 minus. Those are all examples of amphiprotic species, and that's because they have a hydrogen, so they could lose that hydrogen and be an acid, or they have a negative charge, which means they could also accept a hydrogen, at which point they are being a base, okay? So again, we're going to talk about amphiprotics throughout the unit. For the most part, it means it can be both an acid or a base. It's combining with water or not it's combined with water, it is either water or it's something that has a hydrogen and a negative charge. Okay, so let's revisit some of those Chem 20 calculations. So we can look at calculate the pH of a 2.5 times 10 to the negative 3 mole per liter HCl solution. So we need to make sure that we recognize with a question like this that we need to write an ionization equation. So we're going to have our HClAq. We're going to combine it with water. Okay, this is a strong acid. So strong acids are going to go to completion. So we can use a single-headed arrow. Product-wise, it is going to turn into a chloride ion plus a hydronium. Okay, so we needed to write this because if you think about our pH equation is that pH equals negative log concentration of H3O+. Sometimes you guys want to just see a question like this and throw in that 2.5 times 10 to the negative 3 right into pH. The problem, though, is the equation isn't pH equals negative log concentration of HCl, it's pH equals negative log concentration of H3O+. So that means we need to find the concentration of H3O+. So to do that, right now we were given the concentration of our HCl. So we're just going to do a quick little unit analysis to be able to calculate the concentration of hydronium. So unit-wise, find moles of H3O plus per liter. So we can start with our ratio. So 1 mole of hydronium, and that is going to be over 1 mole of HCl. Okay, we need to get rid of moles of HCl. We need to introduce the liters. So we are going to times by the 2.5 times 10 to the negative 3 moles of HCl per liter. Okay, so looking at our units, we should be able to see that moles of HCl and moles of HCl are going to cancel. That leaves with moles of hydronium and liters. So answer-wise, it was a 1-to-1 ratio. So yes, it is still the same number. So this is where usually someone says, hey, Ms. Chip, why do I have to show all of that work if it's the same answer? And this is where my answer is. If it's a written response, this question would be out of 3 marks. 1, it would be coming from writing this equation. The second one would be coming from this. And the third would be coming from the pH calculation. So if you only did a pH calculation, you only get 1 of the marks. Obviously, if there's a multiple choice or a numeric response, we're not looking to see your work, so it doesn't really matter if you choose to recognize that and do that. But on a written response, if it was out of 3 marks, I would want you to show me all of this. Okay, so now that we have the concentration of hydronium, we can go ahead and calculate the pH because it is negative log concentration of hydronium. Okay, so we're going to do negative log of our answer, so that 2.5 times 10 to the negative 3. I want to say we talked about this when we were reviewing at the very start of the year, but maybe I forgot. Remember, our pH rules are wonky, right? So this has 2 significant digits. That means when I calculate my pH should be going to 2 decimal places, okay? So negative log 2.5 times 10 to the negative 3, I should be coming up with 2.60 as my answer. Okay, if you guys need to pause the video at any point, I should probably said this at the beginning. You can pause if you need to catch up. I will also have this posted on D2L. All the lessons for the next 2 weeks will be posted as soon as I get a chance to make those videos. So you can definitely watch them. If you need to watch them again, you can do that as well. If you need to pause as you go, you can do that. Also, don't hesitate to email me. So far, I'm A-okay. But yeah, so you can email me and I will get back to you as soon as I possibly can, okay? If things do change though, I will definitely keep you guys updated and let you know. All right, so last one is going to be a base question. So it says calculate the pH of a solution made by dissolving 2.50 grams of sodium hydroxide in 500 mils of water. So same deal, we're going to start with our equation. So we have sodium hydroxide. Okay, this is a base. It is a strong base, so a single-headed arrow. Because it's a base, we're going to write water over the arrow. Okay, then this is going to dissociate and is going to give us sodium ions plus hydroxide ions. Okay, so it's asking us to find the pH. We have a base, so we're not going to be able to find pH initially. We're going to have to calculate pOH, and then we're going to be able to convert it over to a pH. But for me to be able to calculate pOH, I'm going to have to determine the concentration of the hydroxide, right? And I need to do that so I can eventually get a pOH so that I can get that pH, okay? So givens-wise, we are told 2.50 grams of NaOH. We are also told 500 mils, which is 0.5 liters. Okay, we need a molar mass, so let's get that. It's going to be 40. So 40.00 grams per mole. All right, so we need to do our calculation. So we are calculating the concentration of hydroxide. So what's this going to equal? We're going to start with our ratio. Why our ratio? Because it has moles of hydroxide in it, and we know we need that. So we're going to say 1 mole of OH minus, and that's going to be over 1 mole of NaOH, right? What we're looking for over what we have. We need to get rid of moles of NaOH. We can use the molar mass to do that. So we're going to go times moles of NaOH, and that's going to be over our 40 grams. Okay, so by doing that, we can now cancel out moles of NaOH. Okay, we need to get rid of grams. To get rid of grams, we're going to times by 2.50 grams. Okay, you can put it over 1 if you want. You don't have to. But if you're like, I like my stoich to always have a top and a bottom, then you can definitely do that. Okay, so now we're going to cancel out grams. So now we look at our units. We have just moles of hydroxide. We need to introduce the liters. So we are going to times by 1 over 0.500 liters. Okay, now that's going to give us the moles per liter that we need. So we calculate this, we come up with a concentration of 0.125 moles per liter. Okay, now we have hydroxide. So from hydroxide, we can calculate our pOH, because pOH is equal to negative log concentration of hydroxide. Okay, so we're going to do the negative log of that 0.125. So the negative log of my answer gives me 0.903, and that number keeps going. Okay, I'm just going to put the ... so that I know that I'm still using that entire number in my calculator. I don't want to round for significant digits until I'm completely done with the question. So now that we have pOH, we can calculate pH, because pH is going to equal 14 minus pOH. So we're going to do 14 minus 0.903, and we can go ahead and get that answer. Okay, significant digits, what do we have? So 3 significant digits and 3 significant digits, so we're allowed to have 3 numbers after the decimals. So we're going to go 13.097. Okay, oftentimes we don't count the 0. Sometimes when it comes to pH, we do count the 0. So I would either accept 13.097 or I would accept 13.09, no, that's not 969. Okay, I would accept either of those because 3 numbers after the decimal, and that 0 sometimes is and sometimes isn't. Realistically, on a diploma, you wouldn't get a question exactly like this one because you could never input this into the numeric response boxes. It would be too many numbers. You're also going to find generally on the diploma when they ask you really simple pH and POH questions, which they will, there's definitely going to be one or two, probably just one, I would say, question. Sometimes it's a numeric, but sometimes it's a multiple choice. But usually it's not as complex as this one. Usually it's more like the last one. Or sometimes it'll be as straightforward as, if this is the hydronium, what is the pH? Or if this is the hydroxide, what is the pH number? So you do want to make sure that even though you need to know how to do all the K calculations that we're going to do in this unit, that you also know how to do some of these simple Chem 20 type calculations, because they are going to pop up throughout the course, right? So one of the big things you want to make sure you do with any acid or base question is first decide, is it strong or weak? Because if it's strong, you're going to do stoic. If it's weak, then you're going to look at doing ice tables like you are going to see tomorrow, okay? So this is kind of your intro to acids and bases, with the exception of the Bronsted-Lowry stuff. Everything else should have mostly been review. Obviously, if you took it second semester, how much of this is review versus new is going to depend on how much you engaged with all of that online content while you were at home. Okay? All right, so again, if you have any questions, send me an email. I will make sure that this video is also posted on D2L, so if you need to watch it again or you just need to watch a certain part of it, you can definitely fast forward to that part or rewatch the whole thing, whatever it is you need to do. All right, take care.